Okay, so we're gonna start exactly where we left off the last time we were together. So we are ready to start looking at selecting spur gears for an application. The first thing we're going to be talking about here is picking the pair and really defining what are all the parameters that are going to meet the needs of our application. So we're going to be specifying when we have a set of spur gears, number one, the diametral pitch. That's that capital P. And that is going to be, as we had talked about last time, that's going to be the size of the tooth. So whenever we have two gears that are in mesh with one another, they have to have the same diametral pitch. So we always have to pick the diametral pitch, and it's the size of the tooth, Pressure angle is also what we're going to be picking. As we had discussed last time as well, we're either going to pick from 20 or 25-degree pressure angle. 14.5 is out there for replacement parts only. So if there's existing machinery that has 14.5, we will replace those. But for new designs, anything that you're, starting from scratch is going to be a 20 or a 25. And then to really kind of round out our design or other specification of our gears, kinematics wise, we're going to be then determining what are the number of teeth on our pinion, the smaller gear in the set, and the gear, the larger gear in the set. So diametral pitch, pressure angle, and number of teeth. So as we go forward here, just a little bit of information on each one of these in regard to each one of those parameters individually. So first, looking at diametral pitch, it is going to be the first parameter that we pick when we are determining, exactly what the gears are that we're going to be picking. So diametral pitch, as we just mentioned, is the size of that tooth. The larger the tooth, the smaller the number. So if I have a diametral pitch of 5, for instance, that tooth is going to be larger, chunkier than a diametral pitch of 16. Okay, so the larger the number, the smaller the tooth, or the smaller the number, the larger the tooth. So if we go back and we look at figure 10.5 on page 265, we really can kind of see lined up here an example of proportionally, not saying that these are the exact sizes, but proportionally, this is a 48, a diametral pitch of 48 small teeth. And then we've got a diametral pitch of 4 and 3 bigger, chunkier teeth. Okay. Again, those gears that need to mesh together and to operate the way we're anticipating have to have the same diametral pitch. Now, if we look at page 10.6, this is going to serve as a guide, as a place to start with what diametral pitch to begin with, because you can't just like, okay, what is my diametral pitch going to be? I don't want to just pick it out of the air. We want to have, some sort of a guidance, like when I'm operating under these conditions, here's the size of the tooth that I should consider. Okay. So table 10.6 does that for us. Now, this table is specifically for mild steel gears, and they're all 20-degree pressure angles. Now, if you have other specifications in terms of the type of material that you're going to be using or a particular vendor that you're going to go with, they will have a chart like this for you to get started. Okay, so this is just kind of a, if you would, run-of-the-mill kind of a generic one. So I'm going to go back underneath here. And on the bottom of page 275 is where you are going to find this table 10.6. Okay. And as it says at the top here, this is suitable diametral pitches for 20-degree mild steel gears that have the standard face width, meaning there is a face width that matches up with the diametral pitch. So for instance, if I have a diametral pitch of 8, that's going to have a set face width, how deep that tooth is, that we're going to distribute that force as we transmit from one gear to the other over that length. And when you go to the next diametral pitch, it's going to have then another. And so they're basing it on the gear standard as far as what the standard face width is. Manufacturers may have their own kind of in between there, offering maybe some other types, but these are for standard face widths. So what we do is we line up whatever the horsepower is for our particular application with whatever the RPM is close to of our pinion or our faster moving gear. Okay, so if we have a application where we have 1800 RPM on that pinion and we're operating at 1 horsepower, you'll notice that right here we come together. This is the number 20. that would be where we would consider starting with the diametral pitch of the gears that we are planning to mesh, okay? You'll notice that as we go down the chart, our horsepowers get higher, which means that we're pushing like more through it. They're going to need to be, you know, transmitting more torque, more horsepower, and rotational speed. And you'll notice that as we go down, these numbers get smaller. So that means we have bigger, chunkier teeth that we're gonna be using for this application. Now, I want to emphasize that this is a place to start. This is a place to start. So if you're looking at a diametral pitch of 20, and you know elsewhere on, for instance, this machine or other designs that you've used or are kind of patterning off of, use a different diametral pitch that is going to be, for instance, maybe something that's a little bit bigger tooth. Maybe it's a 16 or it's a 12. It doesn't mean that you have to go with 20. It's a good place to start. It's where you're gonna get like your guidance, like where do I even begin? Like where, being in the ballpark, if you would, for your design. That's what this table is for, okay? Now, the next thing that we have to consider and we have to make sure that lines up from gear to gear when we're going to be in mesh with one another is this pressure angle. So the pressure angle, as we had talked about and we had seen, is the angle for which that resultant force due to the tangential and the radial forces that are being transmitted through those gears, it's going to be that resultant, and it's its angle to the horizontal, okay? So if we go back, just kind of refresh our memory of pressure angle. We go back to page 264 in our book. Okay. This is where we're seeing these two gears that are going to hit one another. They're going to hit one another and they're going to have contact on that pitch line circle or the pitch diameter. Okay. That's what we call that effective diameter. That this diameter that's going to be created where that engagement occurs is called the pitch diameter, small d. Not diametral pitch. Diametral pitch is size of the tooth, capital P. This is small d, okay? And at that point, the forces are being transmitted. So as we come in at a pressure angle, the two forces that are being transmitted are going to be the tangential force, which is going to be perpendicular to the radius of rotation. And then we also have a radial force, which is always going to go from that point of engagement down towards the center of rotation. Those two are 90 degrees to one another. Okay, so the resultant between those two is going to be the actual force itself. It's the resultant of those two. The resultant of those two is going to be at an angle to the horizontal, which is our pressure angle. Okay, that's where it comes from. Now, let's talk a bit about this angle and as we kind of, you know, talk through 20, 25, and 14.5 even. So 20 is going to be like your kind of run-of-the-mill regular industrial applications. It's where you're actually going to probably start. Okay. And if we have you know, an application where we're running more torque, more force through here, and we have a greater chance of these teeth breaking off, then what we may want to do is go with the 25 degrees. And what does 25 degrees do? 25 degrees is going to increase this angle. So if I increase this angle by 5 degrees, for instance, and I have my resultant coming in at a steeper angle, but it's the same number, what happens is my tangential is going to shorten up. Do you see that? So my tangential, maybe I got to do this so you guys can see it. My tangential is going to be this force going in, and it's going to shorten up. But then my radial is going to come over, and it's going to get longer than a 20. So comparing from 25 to 20, I'm going to get a longer or more magnitude on my radial, and I'm going to get less on my tangential. Why would that be advantageous for an application where I'm going to anticipate that there's going to be higher forces, higher torques that I'm dealing with? More what? Say a different one. Not mass. What am I pushing down through the center where the actual material is? What is this? It's not mass. It's a force. It's a force. I'm going to be pushing this force down through the center of the material here instead of shearing off a tooth. Okay. So if I can minimize that tangential force, that's going to be less force that is going to be wanting to push off or push that tooth over or shear that tooth off. That's why 25-degree pressure angles are going to be ones that we consider for those for those higher forces, low speed applications where you have to just like bigger, chunkier, like, for instance, I don't know, a gearbox for lifting a bridge, for instance. That's going to be an application where we want to have at least a 25-degree pressure angle, okay? Because we want to minimize pushing that tooth over or shearing it off. But when we have smaller applications, like our regular industrial strength ones, where we've got, you know, kind of middle of the road types of torques and horsepowers, then going with 20 lengthens this out a little bit, and then we have minimal radials going down through there, okay? Now, think one more degree, I'm gonna say one more degree, but one more pressure angle. If we do 14.5, this gets more shallow. And now we're gonna be doing that very same thing, but in the opposite direction. At 14.5, we get a higher tangential and less on the radial. And as you can imagine, you have then a higher potential of shearing teeth off, you know, sooner than later. So, so that's why 14.5s are not used anymore for new designs, only for replacement parts for existing machinery. Okay, so pressure angle. Any questions about that?
25 degrees for low speed.
Correct. Yes. Are they? 25. Oh, I must have mixed those up. So low speed, I think that's what I meant to say. Low speed, thank you, Mitchell. This should say low speed and high power. Okay, so it's the bigger, chunkier types of applications where you're gonna see the 25-degree pressure angle. Okay. Yep. Thank you. And gears need to have the same pressure angle in order, again, to mesh together. So diametral pitch and pressure angles have to be the same for the gears. But then what'll be different is going to be the number of teeth. And that's going to be based on the type of and the amount of speed that we need to generate, or the difference in the speeds that we need to generate between the two teeth themselves. So the number of teeth is going to influence that pressure or that velocity ratio, as we saw the last time. Okay. Now, if you recall, the last time we were together, we created a an equation sheet, right? It's up here. Say, wait a sec. You know, I had it. We created an equation sheet. And at the bottom, we saw all the different ways that we could calculate our velocity ratio. And the velocity ratio is the ratio of the speed on the input to the speed on the output, meaning how many times does our pinion, our smaller gear, have to rotate around in order to get our gear, the larger one, to rotate around once? And we can get that by comparing a couple different things. First of all, we can take the rotational speed of the pinion and divide it by the rotational speed of the gear, okay? Or we can then look at the physical traits, meaning the radius and or the pitch diameter. What is the diameters that those are? But notice that our larger number always goes on top. And because physically a gear will be larger than a pinion, the twos then go on top for radius and diameter. And then they're going to be divided by the ones, if you would, on the bottom, the pinions. And then number of teeth, same thing. We're going to have more teeth on a gear just because it's larger. We can get more around that circumference than on a pinion, okay, than on a pinion. So when we look at the number of teeth, they influence the velocity ratio, and that's what that slide says. So if I have more teeth on my gear, I'm going to have a larger, if you would, compared to the same size pinion, I'm going to have a larger velocity ratio, meaning that pinion has to go around more times to get that gear to go around just once. Okay. The number of teeth must be an integer, okay? So we can't have a half of a tooth, for instance, on a gear, all right? And then also in general, the goal is to keep the design compact to try to specify as small of gears as possible. And when that's not possible, for instance, if we need large ratios to be accomplished from the input to the output for an application, then we might have to start looking at kind of stacking these up in a train, as we call it. And that's actually going to be what we look at after we look individually here. But being in a compact design is usually one of the things that we want to do as a designer. Manufacturers do not stock and make all integers. We saw that the last time we were together. If we take a peek back at the chart on page 276, starting on page 276 and going to the next one, here is like an example of the standards in terms of the gears that are made with the number of teeth for standard diametral pitches. So starting with, a 24 diametral pitch, notice that they'll make a 12 tooth gear, then a 15, but they don't do a 13 and a 14. So you can't just, randomly pick numbers of teeth just because they're an integer, because there's a potential that they might not be, created by a manufacturer. Okay. So you need to have kind of manufacturer information in front of you as you're doing your design in order to be able to, pick gears that are going to be available. Okay. And that's that table, most commonly used. So let's look at problem number 10.9 and 10.10 to, kind of apply the things that we just, have been looking at. So in your book on page 276, just above actually where we were looking at, there is example 10.9, and we want to determine the diametral pitch for the concrete mixer gears in example 10.3. So I'm going to go underneath, scooch this up a little bit. So on page 276 is this example. So it says we have a pair of mild steel gears that we've selected for that concrete mixer that was described back in problem 10.3. The mixer is driven by a 10 horsepower engine at a speed of 1800 RPM. Determine the approximate or appropriate diametral pitch. So if we look at that chart on page 275, this one right here, we want to line up the horsepower with the pinion speed. Okay, I got to look back. How much horsepower? I know it was 1800. So it's a 10 horsepower. So we're going to go down, 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 down until we find 10 in that column. And then we're going to go over to the 18. And it looks like they meet at a diametral pitch of 8. Okay, a diametral pitch of 8. Now, as I said earlier, that's a good place to start. All right. So, as you kind of pull things together, you're gonna kind of know, is an 8 okay or not? And a lot of different considerations can go into that. It could be, do we use 8s anywhere else on this machine? Do we get them on a regular basis? Do we feel like they're too big or too small? You may have some personal experience and be like, oh, that seems like it's a little small. I want to go a little bit bigger. But it gives you that starting point. Okay. It doesn't mean that you have to stick with it. It's the one, but it's a good place to start. Oops. Oopsie. Back over there. So as I turn back, okay, they kind of walk you through this process, and you should tell us, oh, a diametral pitch of 8, they wrote it out instead of actually putting the number. So they came to the same conclusion that that's going to be a good place to start. And then you would kind of continue on with the design. When you take machine elements, which will be next term, we kind of continue this conversation, if you would. So we're going to be looking at finishing up the design of the gears. So once we have them picked out, diametral pitch, pressure angle, and number of teeth with this part of the application, the kinematics of it, then we're going to be looking then at, okay, what are the forces that are going to be generated? How high are those going to be? How low are those going to be? What is the material that we're going to be using for our gear? Is there going to be hardness that we have to, put in? And then we'll fill in more variables to finish the design so that we can then, have 2 gears that are going to fit an application and appropriate function for the life we need them to. Okay. So, so that's kind of where we're going with it. But in kinematics, we stop here with the number of teeth, diametral pitch, and the pressure angle. So the diametral pitch in this pair was 8. The number of teeth was picked back in that example 10.3, and then what the like the horsepower is, or the for the application is going to be in there too. Any questions? All right. Then the next example we're going to look at is going to be example 10.10. I believe that's exactly next. Yep, looking at 10.10. So here, what we're going to do, it says we have a speed reducer. Our gear reducer is used on a concept for a small trolling motor for fishing boats. The gears must transmit 5 horsepower from an electric motor that goes 900 RPMs to a propeller at 320 RPMs. Okay, so our input is at 900 and our output is going to be at 320. We want to select a set of gears. So when we talk about a set of gears, just a pinion and a gear, okay, that are going to accomplish this task. So we're interested in, all right, when I go from my input, the 900, my output is going to be going 320. So first things first, we want to determine what is a suitable diametral pitch, okay? So you'll notice that we can see what they already picked here, but let's make sure that we agree with it and find where they got it on table 10.6. So we're going to find 5 horsepower and 900 RPM. We're going to match those two up over here. So 900 RPM is here and 5 horsepower is right there, and they come together, and sure enough, 10 is going to be the number. Okay, so that's where they started. Then what we're going to do is we have a velocity ratio here based on what we have coming in, the input power or the input speed, 900 RPMs. And then we also have our desired output speed. So instead of just looking at their numbers here, let's kind of write this out. Okay, so example 10-10, all right, and number 1 diametral pitch is going to be 10, and that's from table 10.6. Then number 2, we want to determine what is the actual velocity ratio that is based on what they're telling us is the input to the output. So our W1 divided by W2, and this comes from our equation for velocity ratio here, okay? And we're going to use this first part. So we know that our W1 is the 900 RPMs and our W2 is 320 RPMs. Now remember, this is a ratio, so our units are going to cancel top to bottom. So we don't have to do any switching to radians or radians per second or anything like that. We're just going to use common variables or common units top and bottom so that they can cancel out, and we just get our number, our ratio, our velocity ratio. So doing that, what's the number that we get? .2, what did you say? 2.28? 2.8. Okay, all right. So our velocity ratio is going to be 2.8, and I'm going to add on 2.81. Okay. And what that means? No, you tell me what that means. What does this velocity ratio mean? 2.18. 2.18. How would you put that in your own words? So why would I be interested in that? Which one? Which gear is spinning 2.81 times faster than the other? The pinion is, yes, it's going to be the smaller that is mounted to our motor, right? And it is going to be spinning 2.81 times before that gear gets around just once. So as you can see, the pinion is going to be going fast. That gear is going to slow down because of the number of teeth around its circumference. So it's a speed reducer. Okay, this is a speed reducer between the pinion, the input off of that motor, to the output, you know, the trolling motor, right? Okay, so we've got our velocity ratio. Now, you're going to notice that they're going to rearrange their equation because we want to determine what is an appropriate set of teeth for my pinion, number of teeth on my pinion, number of teeth on my gears, okay? But the caveat is, if we're going to be using a diametral pitch of 10, we're going to be going up here, and the only ones that I can pick from are the ones that are actually here, okay? So we want to find what is a set of gears that is going to obtain for us the 2.81 or very close there too, okay? So what we can do is we can set this up so that we can solve for the number of teeth on our gear. Okay. Again, because we're usually starting with the number of teeth on our pin, you're going to start on that left, the lower end, if you would. So if we say our velocity ratio is equal to the number of teeth on the gear divided by the number of teeth on the pinion, that's our equation, right? From here. Okay. Solving for the number of teeth on our gear, I'm simply going to multiply my N1 up here, right? Algebraically. So I can rearrange this to be N2 is equal to, and if I multiply this up, my velocity ratio times N1. Okay. So if I know my velocity ratio is 2.81, I'm going to multiply it by a number of teeth that I can use. So I'm going to go up to my diametral pitch of 10 here, and I can start with any number of teeth here. So I've got 12, I've got 14, 15, 16, 18. And so let's start with 12. Okay, let's just start at the beginning. So this is going to be 12 teeth. Okay. And when I multiply those two out, what do I get? Not a nice number, right? So we get 33.74 teeth. Okay, is going to be equal to N2, right? Well, that's not going to work because there's not something that has 33.74 as a number here. It has to be an integer number. So then what do you think we do next? We try another one. Don't try 16 yet. Look further ahead and see which one they picked. No. So if I say my N2 is going to be equal to, now I'm going to try a new pair. Okay. And this time it's going to be 2.81 times, let's try this one. Let's try 14. Okay. Now, why am I starting with my smaller numbers? What was one of the criteria that I want to keep in mind as I'm creating a gear drive? We want to keep the design as compact as possible, right? As small as possible. So you do want to have, those smaller gears most often. All right. You usually have, space that you have to fit this within. So it's always good to kind of keep it on that compact size. So we'll try this again. 2.81 times 14. What do we get for that one? 39.34 teeth. Yeah. So that one's not coming out exact either. All right. Let's try 16. Let's try 16. So this was kind of these are iterations, we call them. Okay. So N2 is going to be equal to 2.81 this time times 16 teeth, right? Okay. What do we get? Yeah, 44.96. Now that's pretty darn close to 15, right? So if we say, to 45. So if this is 45 teeth, all right, and we recalculate our VR. So if we say VR is equal to, and we'll call this actual, it's going to be N2 divided by N1. So if we take 45 and we divide it by 16, teeth cancels out, right? 45, 16 divide. We get 2.8125, which is actually the exact number that we had earlier. We rounded. Okay. So our pair then would be 16 and 45. Okay. Now, to call this a set of gears, what we need to do is we need to say that our set of gears is, so step number 4 is going to be, we're going to have a pinion, and it's going to be a PD is equal to, a diametral pitch is equal to 10, 20-degree pressure angle, and 16 teeth. Okay, we need those three things: diametral pitch, pressure angle, and the number of teeth. And then our gear is going to be diametral pitch of 10, pressure angle 20 degrees, and the number of teeth here is going to be 45 teeth. Okay, so that would be your answer. Calling out the specifications for the gear and the pinion to obtain that velocity ratio. Yes. What was that? In this case, they did not give us a range. So for instance, a lot of times in an application, you might say, I want my output to be between 200 and 210 RPMs. All right. So you have a little bit of wiggle room there that you can satisfy. In this problem, they just said it had to be 320. So then you're really trying to like nail it down. Yeah. So it depends on what the problem gives you. Okay. But this would be what you would specify kinematics wise for a gear. This like completes the kinematic problem for 2 gears that are in mesh. Then we would take it then the next step further, machine elements. And now we would start looking at material and heat treating and all sorts of things. Looking at the stresses that are created. Okay. But kinematics, we don't worry about that just yet. We're just looking at motion that needs to be achieved. All right, online, does anybody have any questions so far? All right, this is good stuff. Okay, let's see where we're at on our PowerPoint. So that does bring us to the end of our PowerPoint. So next time you're ready to start the first half of the assignment. We actually kind of saw that this actually adds a couple more problems to what you can do. So if we go to the end of our chapter, the next 2 problems that you would be able to do at this point would be numbers 25 and number 26. Okay. So, so the first set of problems, I think there's like 4 or 5 of them. And then now you can add 25 and 26 that are going to directly relate to the problem that we just did. For those problems, use the charts that are in our book. Okay. And they're the very same type of thing. You're going to determine an appropriate set of gears based on what they're asking you for here. Okay. So in this case, it looks like it says as close to 480 as possible. So if you're off by a tiny little bit, you can go with it. But anything more than 5 RPMs, see if you can find something closer. Okay. All right. Okay. Any questions right now? So we're now ready to move and start looking at gear trains, which is going to be our next lecture, next PowerPoint. And so I'm going to go back to our learning plan, and we're going to pull up the second PowerPoint, which is going to look at gear trains. Do I need to? No. We're just going to keep going. So our second part of chapter 10 is going to be looking at gear trains. So gear trains are when we look at a series of mating gears that are used to achieve larger speed reductions. Okay, so sometimes maybe we want to have a reduction, for instance, of 180 to 1. That would mean if we would do it in one set of gears, our gear would have to be 180 times larger than our pinion, which just is like not feasible many times. Okay. So what we do then instead is to achieve such a large reduction overall, we're now going to take sets of them and then we're going to put them together. And so we're going to have 2 gears that are going to work with a velocity ratio. And then you're going to then have them on this, you're going to have a common shaft, and it's going to then transmit to a next set of gears, and then a common shaft and a next set of gears. And this is called a train. So by the time you get to the end of your 1800 RPMs to 10 RPMs, now we've broken it into steps. Okay. So each one of those little parts is going to be an individual velocity ratio. And then that's going to make up a whole train from one end to the other. But then it gives us the opportunity to keep the design compact, as opposed to having this one huge gear that has to kind of do the whole thing. Okay. So a train value is going to be the overall velocity ratio when multiple gear pairs are used in a series. So the equation for a train is simply going to be the velocity ratio of the first set times the velocity ratio of the second set times the velocity ratio of the third, fourth, however many are in our train. So we can add this to our equation sheet. There isn't much room at the bottom of mine, but I'm going to try to sneak it in right here. So I'm going to have train value is going to be equal to velocity ratio 1 times velocity ratio 2 times velocity ratio 3. And then I'm going to put this for however many there are. If there's 8, we do 8. If there's 2, we do 2. If there's only one velocity ratio, then it's not a train value. It has to have multiple. So once we start getting 2 velocity ratios, then it becomes a train. Okay. So TR is equal to train value. Now, because these velocity ratios are each ratios, there aren't any units associated with a train value. Okay. It's just, again, going to be that difference between our input and then we go down the train. And then what is the output, the input of the output? Okay. All right. A transmission in a car, gear train. Okay. All right. Let's look at an example. Okay. So let's do this once together. This is example 1018. And this is going to be found starting on page 288. Starting on page 288. And here it says we want to determine the rotational velocity. We're going to call it W7 of gear number 7 as gear 2 drives at 1800 RPMs counterclockwise. We want to also determine what is the center distance between the shafts carrying those gears between gears 2 and 7. Okay. So as we look here, here is the illustration for the problem. Now, what we're seeing here is this is considered, if you would, the front view of our gears, and then this is looking down at the top of them. So in projection, this is the center line of our shaft, which is then the center of gear number 2. Okay. Gear number 2 is in mesh with gear number 3. Notice how it got larger here. So in this set, 2 is the pinion, 3 is the gear. Now on that same shaft in front of it is going to be gear number 4. Gear number 4 is in mesh with gear number 5. Okay. So in this set, you'll notice that 5 is bigger. So then 4 is the pinion in this set. But again, 4 is going to be going at the same rotational speed as number 3. Then we've got 5. In front of 5 is gear 6. Gear 6 is engaged with gear 7. As we look, gear 6 is physically smaller. This will be our pinion. And then gear 7 is going to be our gear. All right. And then that'll be the last gear. So what we want to know is what is the difference in RPM from our first to our last. So this is going to be, if you would, our input. Okay. And this is our output. Now they're telling us in this problem that gear 2, and it's up on the top of the next page, gear 2 is going at 1800 RPM counterclockwise. Okay. Counterclockwise. So that means that this is going to be W2 is equal to 1800 RPMs. Okay. Going counterclockwise. And part of what we want to find, the first part we want to find is, okay, what is the rotational speed counterclockwise, clockwise of W7? What's going on there? All right. What's going on there? Rotational speed wise and direction. And then the other part of this problem is, what is the center distance between these two? What is the center distance between these two? Okay. So that's what we're going for. So I'm gonna kind of start a new problem statement here. Okay. So this is sample 1018. So our knowns are W2 is going 1800 RPM and it's going counterclockwise. And the other knowns that we have are actually listed at the top of the next page. Okay, they're giving us information about each one of the gears. So 2 through 7, we're going to find out, you know, some information, whether it's number of teeth, diametral pitch, pitch diameter, they're gonna let us know. All right. So we've got some other known. So known plus known gear info. Okay. And that's at top of page 289. Okay. And then what we want to find is we need to find what W7 is. And we need to find what the center distance from 2 to 7 is. Okay. From 2 to 7. All right. Now, what we're going to want to have handy is going to be the equation sheet that we created. Okay. So when we look at center distance, notice that we have two options here. We can either go with the radiuses or the diameters, divide by 2, or we can use number of teeth and diametral pitch. Okay. When we're looking for what is the end result of all of our speed ratios, okay, we're going to be looking to velocity ratios and this train value, okay, and finding out, okay, as a train from the input to the output, what's going on so that I can predict how fast W7 is going, okay? And to get any one of those velocity ratios, we have these as options, okay? So as you can imagine, this is going to give us a nice variety of using these equations, which is nice, okay, which is good, comprehensive. So as we look here, let's look at our knowns, okay, what we have in terms of each one of the gear information. So right now, we know that for gear 2, we have the number of teeth as 12 and a diametral pitch as 12 as well. And then number 3, which it is engaged with, has a pitch diameter of 2.5. Okay. Now, as we look at the arrangement here, we have one set of gears. Okay. So this would be our velocity ratio number 1. Okay. That would be the first velocity ratio, the first set of gears that we have in this train. The second one is going to be between these two. That's going to be our velocity ratio number 2, which is going to be between 4 and 5. And then we have the third velocity ratio between 6 and 7, velocity ratio number 3. So to get the full train value from one end to the next, we'll multiply V1 plus V2 or VR1 plus VR2 plus VR3, okay? But first we have to get those individual velocity ratios, okay? So our train value, if you would, is going to be equal to each one of these multiplied together, okay? So to get our velocity ratio, gotta look back over here. Velocity ratio, we can use any one of these, right? We can use any one of these. So for gears 2 and 3, these two are in mesh. We've got number of teeth of 2, but we don't have the number of teeth of 3. We have the diametral pitch of 2. We do have the diametral pitch of 3. Why? How do I know that the diametral pitch of 3 is 12? I do know that. I'm positive about that. They have to mesh, right? They have to have the same diametral pitch. So we know that the diametral pitch is going to be the same for these, but I don't have, whoopsie, I don't have the number of teeth of both, or I don't have the pitch diameter for both. Okay. So what do I need to do here? Figure it out. And I got to choose which one that I want. Now, because of, you got to think ahead a little bit here, because I also want to know center distance. Okay. Center distance is going to be dependent on radiuses. Do you see that all the way through? So because I am given a pitch diameter for number 3, I want to find the pitch diameter D for number 2, so that when I when I need to do it and figure out my center distances, I can just divide it by 2. You could do numbers of teeth between these and do numbers of teeth, but then you're going to end up calculating for a diameter later on anyway. So why not just do it right away? If you didn't have to worry about center distance, you could do either one of them here. Okay. Does that make sense to everybody? Okay. So because we are going to be doing the center distance, okay, center distance, notice how if I want to find the center distance between these two, it's going to be the radius and the radius, right? And I'm given the diameter for number 3 already, so I can figure out its radius easily. If I figure out the number of teeth for this one, I know that I have to find the center distance all the way over here. So I might as well kind of plan ahead and do the pitch diameters for each one of these. So then I can just add up the radiuses to get the center distance from 2 to 7. Okay. If the problem wasn't requiring the center distance from 2 to 7, then I wouldn't have to, worry about which one I would calculate. I could just figure it out. Does that make sense? All right. So what we're going to do with that in mind, then we're going to figure out what is the pitch diameter, small d, for gear number 2. Okay, for gear number 2. Now to get that, here's my equation. Okay, here's my equation. So for my first set of gears, I am going to say that step number 1 is going to be determining the pitch diameter of gear number 2. Pitch diameter of gear number 2. So I need to rearrange this equation. That means that I'm going to multiply my pitch diameter up and my diametral pitch is going to come underneath, right? So that's going to be equal to the number of teeth on my number 2 gear and the diametral pitch of that gear as well. Both of which we are given in our problem. So we know the number of teeth and we know the diametral pitch. So now we're just going to put in number of teeth is, what did it say? 12 and 12. 12 teeth and 12. Now remember, they don't give us anything but a number here. What are the units for diametral pitch? Teeth per inch, exactly. So you want to put those in there so that you make sure that you end up with the appropriate units, okay? So my teeth are going to cancel here, and I have the inches in the denominator of the denominator, so my units left over are inches, which those are good for a pitch diameter. So you can see here that D2 is going to be equal to 1 inch, right? Okay. So now, over on the side here, I can calculate the velocity ratio, right? Because I need the velocity ratio between those two. So velocity ratio, I can take the pitch diameter of the gear in this set, which is gear number 3, divided by the pitch diameter of the pinion in this set, which is pitch diameter number 2. So my velocity ratio number 1 is going to be pitch diameter of gear 3 divided by pitch diameter of gear 2. Does that make sense to everybody? Because this is our gear, this is our pinion. Okay. So here, when we look back at the information given, number 3 has a pitch diameter of 2.5. Okay. So this is going to be 2.5 inches divided by 1 inch that we just calculated here. Okay. So that's pretty easy. Velocity ratio number 1 is going to be 2.5 inches cancel. So we're going to need this. I wouldn't put maybe necessarily a box underneath it because it's not a final answer, but it's something that we're going to need for that train value. And now we have the diameter, the distance for that first gear. Okay, any questions so far? Now we want to work to our next velocity ratio, which is going to be the velocity ratio number 2 between gears 4 and 5. Okay, between 4 and 5. So now we're going to look back at what do we know here. So it looks like we've got 15 teeth on number 4, and then we've got a pitch diameter of 3 on 5 with a diametral pitch of 10. Okay, so between these two, we've got the pitch diameter. So we're going to want to do pitch diameter up here for number 4, but they're only giving us the number of teeth. Or are they? What else do we know about number 4? What else do we know about number 4? We know the diametral pitch because for those two to be in engagement with another, 4 and 5, they have to have the same diametral pitch, okay? So we also know that the diametral pitch up for number 4 is the exact same thing, okay? So now let's calculate the pitch diameter for number 4. Go ahead and do it, and we'll compare answers. Was it 14? Oh, no, it's 15. See, don't copy my number. It's 15 from the problem. So for the diameter, did you get 1.5 inches? Good. And now we can use that over here for our velocity ratio number 2, okay? This one, our diameter on top needs to be the gear. And in this set, the gear is going to be number 5, which is the larger of the two. So if we go down, the gear number 5 is given to us, pitch diameter is 3 inches. So this is going to be D5 divided by D4, okay? Gear and pinion. So this is going to be 3 inches. And then 1.5 inches. Cancel those two out. Velocity ratio here, number 2. What do we get? Get 2. Makes sense, right? Half of 3 is 1.5. All right, oops. We got here. I've got a chat message. So is the only time that we don't have matching pitches when we have 2 gears that have the same shaft, but not meshing? Correct, Jason. Yes. Yeah, if they're in mesh with one another, they have to be the same diametral pitch, but because, and that's a great question, but because, as we see here, diametral pitch for this pair was 12, right? For our first ones. Diametral pitch for the next pair is 10 because they're in mesh, but they're on the same shaft, but they're not engaged with one another. So they can be different diametral pitches. Yes. Good. Yes.
They all have to be the same.
No. Only the ones in mesh have to be the same pressure angle. Yeah. So these two would have to have a 20-degree pressure angle. These two could have a 25 if you wanted them to. Yeah, it wouldn't have to. And sometimes what ends up happening, and really, you'll notice that here, they are doing that. So as we move through, and this will be something that comes more out in our machine elements class, you'll notice that we start with, on the input, smaller teeth. Our diametral pitch is larger, so this is smaller teeth. We have larger teeth at the end, diametral pitch of 8, okay? Progressively, what ends up happening as we go through this design, we're reducing the speed, but we're increasing the torque, which means we're doing more work as we get closer and closer to that output. So it's going to be pushing higher forces through those teeth. So you'll notice that we gradually get larger teeth at the end. Okay. And that's very typical. So, so having that ability to, use different teeth, but only the ones that are in mesh with one another have to be the same. Yeah, that makes sense. Good, good. I'm glad. All right. So that's number 2. Let's do number 3. Go ahead. Figure out whichever pitch diameter you need for our velocity ratio of our last set of gears, which is going to be between gear 6 and gear 7, right? Gear 6 and gear 7. So this is going to be V3. I'll do mine on the side here, and then we'll compare. Okay. So velocity ratio number 3 should be 2.667, right? Oh, no, inches, cancel. Sorry, they cancel out. I was in pitch diameter mode. So it's a ratio, the units cancel out, okay? So now what we need to do to get closer to figuring out what the rotational speed of 7 is we need to know what is the total train value from our input to our output, okay? So the next thing we're gonna do is number 2, train value is gonna be equal to velocity ratio number 1 times velocity ratio number 2 times velocity ratio number 3, okay? And we have all of those numbers right here. So 2.5 times 2 times 2.667. And unitless for each one of these. Oops. Did you get 13.335? Okay. So now remember, train value, kind of going back to our picture over here, is going to be what is the difference in rotation between number 1, or I'm sorry, I shouldn't say number 1. This is actually gear number 2 and then gear number 7. Okay, so what is that difference? So we want to know what is the rotational speed here of number 7. Okay, so now that we know that our total train value is 13.335, that means, okay, that means that on my input, this has to go around 13.335 times before this one's going to go around once. Okay, that's the difference in the speed. So the train value really acts just like a velocity ratio, but we've lined these up to work together. Okay, now we've got more than one, velocity ratio. We have 1, 2, 3 sets of gears that are accomplishing a total speed ratio called the train value. Okay. All right. So now knowing that, and we can really say that if a train value is like a velocity ratio, we can set these two up, right? So we can, I'm going to turn this over. We'll kind of do, this is going to be step 2 continued. We can say our train value is going to be equal to our W2 divided by our W7, right? W2 divided by W7. So we know that our W2 was equal to 1800 RPMs, right? We don't know what W7 is, but we do know that that train value overall is 13.335, right? So as we look right here, as we look right here, our only unknown is the W7, okay? Go ahead and solve for W7 and see if we get the same value. You get 134.98. They rounded up to 135, okay, which is reasonable. Now, there is something that goes along with this that we need to also identify, and that is going to be the direction of rotation of W7, okay? Now, something that they do in the book, which I think is good, and I don't think it's a bad thing. I didn't add it here. I probably should have. I kind of forget about it once in a while, but it's easily determined in these 2 different ways. So you're going to notice, and we did see this negative pop up when we learned about train value, or when we learned about velocity ratio. So train value here, you're going to notice when they multiply their their first velocity ratio times their second times their third. And all they did was, instead of calling it a 1, 2, and a 3 like we did, they called it between the two gears, like a 2 to 3 and a 3 to 4, or I'm sorry, a 4 to 5 and a 6 to 7. So this was R1, R2, and R3. Now, notice that here they put a negative in front of each one. And as you may recall from the last time we had our time together, I said that the negative was not there for any other reason than to say, when I have two gears in engagement, their direction reverses. So if the input is going clockwise, then the output is going counterclockwise, all right? Now, if we put a negative in front of each one of these and we multiply, for instance, a negative times a negative, it becomes a positive, right? And then multiplying again one more time, it becomes negative. So notice that their train value is a negative 13.33, okay? All that means is, well, you tell me, what do you think that means based on what we just kind of talked about? What do you think the negative in front of that 13.33 means? Go ahead, Jacob. Correct. So on our original input, we know that this is 1800 RPMs going counterclockwise. Because this came out to be a negative train value, a negative value, that means that W7 is now going to be going in the opposite direction of whatever that input was. What do you think the value would be? What do you think the direction would be if it ends up being a positive value? So for instance, if we add in a fourth velocity ratio, and this comes out to be a positive number, what does that mean? Then it's going to be the same direction. It's going to be the very same direction. So that would mean that whatever that next set was, now it's going to be mimicking that direction of the input. Okay. And you want to know that. All right. That's going to be important, based on, the directions that you need for the operation. Now you can get it through the math using the negatives, which I think is kind of a nice way to do it, but you can also get at it by just looking at it. You can be like, oh yeah, opposite, back, and then opposite. So you can do it either way. I don't require the negatives because I think sometimes some students, if you forget it or if you're like, oh, it doesn't make sense to me, it's really just there as an aid to confirm the direction. That's all that it's there for. So whether you use it or not is totally up to you. I don't always use it. I forget about it, honestly, because I can usually see what's going on. Okay. But this is a nice little check on that. Any questions? So if you're wondering what that negative is, that's what it is. It's just to determine, the direction compared to the original input. All right, so now that we have our train value, we know what our RPMs for our W7 is. Now the last task here is to figure out what is that center distance, okay? Now center distance, as we look here, is simply going to be the radius of my first gear or pinion, plus the radius of my second, plus the radius of my third, plus the radius of my fourth, fifth, and sixth gears here. You see that? So all we need to do, because now we strategically found the pitch diameters for each of the values we didn't know, and we know the pitch diameters for the other ones that were given, we can now simply take all of these pitch diameters, add them up, and do what to find a center distance? Divide by 2. Yeah. So go ahead and see what you come up with for your center distance. So you should get a center distance of 6.75. Did you guys get that same number? If you added up all the diameters and divided by 2? Yes, no? Okay. All right. And that's the problem, okay? So looking at gears that are in a train, so when we have more than one velocity ratio, more than one set of gears that are trained together or sequenced together to obtain, something other than, just one velocity ratio. If we multiply those velocity ratios to get a train value, and then using that train value, then we can, figure out what's going on the other side, as well as center distances, based on the physical sizes. Yes. The pitch diameters?
The share, we might have the share.
Well, this is the center point between these two, right? So if we go from this one to this one, here's its radius, right? Then we go from here to here, this is this radius. Now for number 4, here's its radius where it meshes. And then number 5, here's its radius. Number 6 to just here, and then 7, because they're overlapping. Is that what it is? Yeah, so here is the point of contact for each one. So this right here, do you see it now? Yeah. I understand, yeah, because they overlap, it looks a little weird. Mhm. Yeah, I know, gears are cool. They're like surprisingly, like there's so much there. They're so simple, but yet there's so much there. Yeah. Okay. Any other questions? All right, okay, so that's going to mimic the second to last problem that you have in your homework, but there's one more type of problem and one more type of a gear that we want to look at, and that's going to be an idler. Okay, that's going to be an idler. So I'm going to go back to our PowerPoint. And idlers are kind of neat, okay? An idler gear, the only purpose of an idler gear is it's going to be used to change the direction of the motion. So let's say we get to where we have our train value, we have our velocity ratios figured out, but we need the output to be in the same direction as our input. And when we do it, there's 3 velocity ratios and it comes out that it's going to be opposite. So what we do is we add in an idler gear, okay? And the idler gear does not change the velocity ratio. The only thing that it changed, there's 2 things that changed. One thing it changes, it's going to be the center distance, because we're going to be adding in an idler, it's going to get a little bit longer. The second thing, and usually the reason we do the idler is because we want to change the direction of the rotation. So we want it, for instance, to be in the same direction as that input rather than opposite, okay? So to do that, or to show an example of that, is we have this right here. So we have gear number 2, we have gear number 3, and we have gear number 4, okay? And notice that as we look here, gear number 3 is going to be what we call our idler, okay? Because gear number 3 meshes not only with number 2, but also with number 4, okay? Also with number 4. So as we look here, if we wanted to figure out the 2 velocity ratios between these 2, all right? We know that, and we'll use the physical size, we would call this velocity ratio number 1 and velocity ratio number 2, okay? And go like this. We will notice that for velocity ratio number 1, it's going to be equal to the pitch diameter of the gear, which is going to be 6 inches. I'll do it this way. I'll put the D3 divided by D2. Okay, so our gear on top, our pinion on the bottom for the first set here. So that means that this is going to be 6 inches divided by 2 inches. So velocity ratio number 1 is going to be 3, right? It's going to cancel out. Then the next velocity ratio number 2 between these two, okay? So velocity ratio number 2 is going to be equal to the diameter of 4 divided by the diameter of 3, because 4 is the gear, 3 is the pinion in this case, right? Smaller and larger. So here, 4 is going to be 8 inches and 3 is going to be 6 inches. So the velocity ratio number 2, what is this number? 0.75. Is that right? No, 1.5. 1.5. Somebody do it on a calculator. It's what? 1.3. Thank you. 1.333. Okay. All right. 1.333. Now, the train value, okay, when we go from 2 to 4, okay, our train value is going to be equal to our VR1 times our velocity ratio 2. Okay, and we'll put the negative in front to kind of show this, right? So if I do that, this is going to be a -3 times a -1.333. What is my train value between the two? What's the number? 3 point what? 3.9. Okay, so yes, you're right. We'll round to 4. Thank you. 4. All right, we've got a velocity ratio of 4. And notice that it's a positive number. So that means that from our input number 2 to our output number 4, they are going to be going in the same direction. They're going to go in the same direction. Now, what I want you to do is I want you to do one other thing. Let's take the idler out. Okay, let's take the idler out. So if I take the idler out physically, my velocity ratio from 2 to 4 is going to be the diameter of 4 divided by the diameter of 2. Okay, so my diameter of 4 is what? 8 inches. And my diameter of 2 is 2 inches. Velocity ratio, if I went directly from 2 to 4 and left 3 out, took my idler out, it's 4. But it's a -4 because of the direction, right? So do you see how train value wise, I didn't change anything. The only thing I did was I added my idler number 3 in the middle so that it would change the direction to be in the same direction as my input. I give up a little bit of distance, but I get the motion in the same direction. So an idler is only for that purpose. It doesn't change the train value at all, because if I would do a velocity ratio directly from 2 to 4, it's exactly the same number as when I did 2 to 3 and 3 to 4. Do you see that? So I could stick in a 1-inch idler here. I could stick in a 10-inch idler there. It's not going to change anything about the train value or the velocity ratios. It's only going to change the direction and change that distance, that center distance. Okay, so idlers are used for only that purpose, okay? So the last problem that you're going to do is going to be an idler problem. And let's look at one that'll be similar to kind of set you up for that. They don't have an example here in the book, so I picked one of the problems in the book, okay? So the problem that we're going to look at is going to be problem 1051 on page 297. So I'll try to get this in here like this, okay? And this problem says that we have a gear train as shown right up here. The gears have the following properties, all right? So they have them listed a little bit differently. So N2, the number of teeth on 2 is 16. The diametral pitch is going to be 16. Okay, so these two go together. And then notice that 2 is an engagement with number 3, and they're giving us the pitch diameter of number 3 only. Okay, then you've got number 4 is engaged with number 5. Okay, so number 4 has a pitch diameter of 1.5 inches, and then number 5 has 50 teeth and a diametral pitch of 10. So that means diametral pitch of 10 is going to be on 4 as well. Then notice that our next one is number 6. Number 6 is engaged with number 5 as well. 5 is an idler. right? 5 is an idler. So now you'll notice for number 6, they give us the pitch diameter of 5.5. Then number 7, 1.5 inch pitch diameter, diametral pitch of 8. And then number 8 has the number of teeth of 56 inches or 56 teeth. Determine the velocity of gear 7. So I'm sorry, I have 7 on my mind. I want to know what W8 is. Okay, so W8 is a question mark. All right. And then also the center distance all the way from 2 to 8. What is that? Okay. So same process is going to occur as we did on the last one, except one thing. And I'm going to wait to tell you that because we'll talk about it. Okay. So let's go ahead and approach this the exact same way that we did the example problem that we just got done with. And what we need to do is, because we're going to be figuring out center distance here, then we might as well find pitch diameters for anything we don't have, right? So we'll take that very same approach. So I'm going to try to put this here. So this is problem 1053. Now 1053, you don't have to do for your homework, but you do have to do the one above it, 1052. So it's going to be similar to that one. So that's why I want to give you an example of this. Okay, so we're going to start with finding the pitch diameter of gear 2. Okay, we know the number of teeth, and it gives us the diametral pitch of 16. So that means that we're going to have N2 over the diametral pitch, and we know the number of teeth to be 16 teeth divided by 16 diametral pitch. Teeth per inch. So our teeth cancel out. We have inches. So D2, 16 divided by 16 is 1 inch. Okay. Now we might as well do the velocity ratio between these two because we know we're going to need it. So I'm going to call that velocity ratio number 1 again. And that's going to be the diameter of gear number 3, the gear, divided by the diameter of gear number 2, the pinion. So gear number 3 in the problem told us it was 8 inches divided by 1 inch. Inches cancel. So it looks like our velocity ratio number 1 is going to be, and we'll put a negative in front of it. Let's use that negative and we'll kind of see how that works out for us. Okay. So we'll kind of put a line underneath that because we'll reference that in a little bit. All right. So now we're going to go to the next set. Our next set is going to be 4 and 5. 4 and 5. So looking at our problem statement, number 4, we have the pitch diameter 4, so we'll use that. But then for number 5, we need to calculate the pitch diameter based on 50 teeth and diametral pitch of 10. So D5 is going to be equal to the number of teeth in number 5 divided by its diametral pitch. So this is going to be 50 teeth. I know I've got like no room here. There we go. 50 teeth divided by diametral pitch of 10. I like the capital T's better. And that's going to be teeth per inch. So my teeth cancel out. And it means that my pitch diameter number 5 is 5 inches. 5 inches. Velocity ratio number 2 is going to be diameter of 5 divided by diameter of 4. So we have 5 inches divided by number 4, which was 1.5. So VR going to be a negative. You guys tell me. 3 point what? 3.3 repeating. Okay. All right. Now we need to do between 5 and 6. Between 5 and 6, right? Here's another point of engagement. So between 5 and 6, we know 5's pitch diameter. We know 6's pitch diameter. It's given to us, so we don't have to do that one. Then we've got between 7 and 8. between 7 and 8. So for number 7, we have we have a pitch diameter and diametral pitch. And then for number 8, we have number of teeth with the same diametral pitch as number 7. So we need to determine the pitch diameter of number 8, which is going to be the number of teeth of number 8 divided by its diametral pitch. So its number of teeth was 56 divided by, I think it was 8. Yes. So D8 7. Okay. Now, velocity ratio, I skipped one actually because we didn't have to calculate it. Let's do our velocity ratio number 3, which is going to be between 5 and 6. So velocity ratio number 3 is going to be the diameter of 6 to the diameter of 5. It's equal to the diameter of 6 was 5.5. And the diameter of 5 was 5. So velocity ratio number 3 will be a negative 1.1. Is that right? 5.5, yep. And then, now that I have the pitch diameter for number 8, I can do the velocity ratio number 4. It's going to be the pitch diameter of 8 divided by the pitch diameter of 7. So the pitch diameter of 8, we just calculated 7 inches. The pitch diameter of 7 is 1.5. Oh. That should be D7, not N7. D7, so 1.5 here. Inches and canceled out. And then VR4 going to be 4.667, and then put a negative in front. So in case you need time to catch up. All right. So now that we have all the pitch diameters done and we calculated the individual velocity ratios here, okay, we've got 1, 2, 3, 4, because we have 4 points of engagement, 1, 2, 3, and 4. Okay, those are the velocity ratios. Now, what's the next step that we're going to do? We have to find out what is the rotational speed of 8, and then what's the center distance. So what's the next thing we're going to do after we've got all our velocity ratios? Yeah, find our train value, exactly. So now step number 2 is going to be, what is our train value from 2 to 8? Okay, train value of 2 to 8. So we're going to take this first velocity ratio, number 1, times the velocity ratio, number 2, velocity ratio, number 3, and the velocity ratio, number 4. Okay, and then we'll put their values in, including the negative this time. So this first one's going to be negative 8. The next one is going to be a negative 3.333. The next one is going to be a negative 1.1. And the last one's going to be a negative 4.667. Okay, bless you. So now looking at, even before we put the numbers in, if this is going to be a negative times a negative positive, times a negative, negative, times a negative one more time, it'll be a positive value. Okay, so you don't necessarily have to put those negatives in when you do your numbers, because you know now it's going to be a positive value when we get done. So our train value is going to be a positive, what's our number? Yep. 136 point, I got 885, right? 136.9, right? No units here. No units here. Okay. We know it's positive. So all that tells us then is direction-wise for W8, it's going to be going in the same direction that the input was. And for this problem, it said that gear number 2 is going 1200 counterclockwise. So our W8 is going to go counterclockwise as well. All right. Next thing, now what do? We need to find the speed of number 8. This should help us. Using the train value, right? Our train value is going to be equal to W2 divided by W8. We know what W2 is. We know our train value. We need to solve for W8. So I'll do that rearrangement here. So W8 is going to be equal to W2 times our train value. Or, I'm sorry, divided by our train value. So you leave it as RPMs, and then we're dividing by that train value, which is unitless. So we end up with RPMs for W8. That's exactly what we want. So what is that number?
8.77.
Units. RPMs, exactly. And that's going to be equal to your W8. So make sure that you add that. And then also add counterclockwise, because we need to know that direction as well, because it's going in the same direction as W2. Okay. Yeah, so that means that this is slowing way down, right? And it kind of makes sense because W2, or I should say not W2, gear number 2 has to rotate 136, 137 times before gear number 8 is going to even go around once, right? Yeah, it's working hard. All right, last step is going to be center distance. Go ahead and calculate your center distance. See what you get. Did I do that wrong? No, we got a different number. No, same. Did you all get 17.25? Jacob did. Eric? Mitchell? Eric, you did? Mitchell, did you get it? What was that? Yes. If you didn't get 17.25, whoops, let me see. There's something in the chat. Let me see. Yes, you got it. Good. If you got it right away, that means that you remembered the idler. Okay. You remember the idler, and the way that it's positioned here, we have to take the diameter because it's an engagement on one side and the other. So if we look here at what's going on, we go from the center line of 4, that's the radius of 4, but then we go to the center line of 5, and then back to the center, from that center line to 6. So we take the entire distance across of 5, okay? So it has to be the full diameter of 5. That's the only one. Otherwise, the rest of them are their radiuses. And the only thing that this idler did here, again, was change the direction. If we take that idler out, we gain 5 inches, okay? But then the direction from the input to the output is going to be opposite, okay? And in this case, it's the same. So that's what you have to be aware of. So for the last 2 problems that you're going to be doing, they're just above here, okay? You're going to be doing number 52. So that is going to pair with this example, this very last problem that we did. All right. So make sure that you remember that idler, different numbers. And then for number 50, you're at the bottom down here. And this is going to be like that second to last problem that we looked at in finding the velocity of that last gear with relationship to the input, finding the train value. But in this one, there's no idler. So this is going to be radiuses all the way. Okay. So that takes us to the end of this chapter, this module. So here we did idlers, we did problem 553. So now you're ready to complete all of the assigned homework. Okay. So you want to see the assignment for the applicable problem. So we've really kind of already prefaced that, but if you want to go back to module number 4 and look at assignment number 4, these are the problems that are in the back of the book. So today we finished up really the rest of them. So numbers 25, 26, we're selecting gears. Numbers 50 and 52 are doing the train value stuff. Okay. And then the ones that are above here were from the last time that we were together. So you should be able to complete everything here. You will notice that there is a homework answer key, just final answers. You know, but may always kind of take a peek, make sure that you're coming up with those values. If not, then don't hesitate to ask any questions. And then this is all considered, you know, written work that we've been doing here. There's no, you know, Excel spreadsheet or computer program to help us with it or any CAD that you have to do. So just make sure that as you're writing, make sure that it's nice and neat, that I can follow it. If you need to, I kind of like going down a page, you know, kind of like chronologically, vertically. But if you end up kind of going in different places, then just number your steps for me, please. That just makes it easier for me to follow. Make sure you include your units in all phases of the problem. If you're wondering what I'm looking for, this is what you do. You look at how we did the problems together, okay? You want to write every equation in variable form before you put any numbers in place. When you put the numbers in place, make sure that you put your units in and then cancel or combined as applicable, all right? And again, make sure that I can see everything. Here's the equation in variable form, equations in variable form, numbers in and such. Eric, do you have a question? Oh, okay. So if you, like I said, if you're wondering what is she looking for, duplicate this process, exactly what you see here. And that's what I'm looking for. Okay. Put a box around your final answer and make sure that your final units are in there with its variables. So for instance, what I mean by that is when we look here at the train value or at the W8, we use the train value equation to get it. We put our numbers in. And I don't just want a box with 8.77 RPMs on it. Okay, what is that? I want you to answer the question. So you want to know, what is W8? What is the rotational speed and direction of gear number 8? So make sure that you tell me what that's equal to. Don't just put a box around it and be like, I'm done. Okay. I take points off for that. Intentionally answer that question, or tell me why you're putting this box around here and what is it for? Okay. I know it seems a little ticky-tack, but it's those little details that just solidify that I know that you know what you're doing. Okay. That you know what you're doing. All right. Any questions as we kind of look at the homework or the work that we've done, the examples? I believe that you do have examples through the problems that we've done that are going to pair up with every single one of these problems. Okay. So don't be afraid to look at your notes. Don't be afraid to look at the book, the examples that we've looked at there. They'll be able to help you. And then I'm here as well. Okay. So, so that's all that I have for today. I'm gonna stop sharing for a moment. Stop sharing. Online, does anybody have any questions at all? All right. In the room, do you guys have any questions at the moment? You guys don't look like it. I don't think so. Okay. If not, Alan's all set. Good. If not, then that's where we're going to stop today. Okay. Jason is all good. Awesome. That's where we're going to stop today. You're welcome. All right. I'm going to stop recording.